Okay, so talking about chemical reactions, this is one of my favorite things to do, and we're going to be balancing some equations today. And so we've already talked about how elements react with other elements. We've talked about ionic compounds and covalent compounds. So we are now going to talk about how compounds interact with each other. And these chemical reactions that happen don't just happen willy-nilly. There has to be a reason, and it has to be very perfect situations. There's no guarantee that something's going to happen, even if it sometimes does. It doesn't always happen. And so what causes a reaction to occur is that when one of those species has a greater tendency to lose electrons than the other. So we can kind of link this back to electronegativity. Typically, these reactions happen now with species, though. It doesn't necessarily have to be each atom. And so what I mean by species is I'm just going to use it as a generic term for both neutral and charged particles. And I wanted to give a quick example here. So in this equation with sodium and water lies my first typo, which that underscore should be a plus sign. But if I were to talk about the species, on the left side, we have a neutral sodium atom. With water, it actually is a H plus as well as our hydroxide ion. And then on the right side, we have now a sodium ion, then another hydroxyl as well as hydrogen gas. And so all these species, no matter if they're neutral, charged, have one atom, have multiple atoms, I'm just going to call them species. I just wanted to give it an example. And so this is something that no matter what you learn throughout science, but especially this class, if you're going to remember one thing, is that no matter what, you have to follow the law of conservation, which I think you guys have probably heard of in other science classes. But just as a reminder, new atoms cannot be created or formed, and old atoms cannot be destroyed. So I'm sure, like I said, you've heard this in multiple ways, but it's so important to remember when we're balancing and when we move into stoichiometry on Wednesday, nothing can be created or destroyed of matter. And we have to make sure to represent that with the stuff that we write as scientists. So the reactions must be balanced. So we make use of coefficients. So let's talk about writing chemical equations. All a chemical equation is a symbolic representation of a chemical reaction. And I'm going to abbreviate reaction, RXN. You're more than welcome to use that abbreviation as well. Again, I'm going to stress this a lot, needs to be correctly balanced. I want you guys to get so good at balancing that you can look at an equation and say, hey, that's not balanced. So that's my goal here. And so how these chemical equations are set up is we have reactants on the left side of an arrow, and then we have products on the right. So as you would assume, reactants are the species that get mixed together, then use the arrow to represent that whatever reaction happens, and it goes and creates some sort of products. What did you produce? So in the example that I was talking about the species, those highlighted in red are the reactants, and then the ones I wrote in purple are the products. It's just more broken down into species. You could say the same thing for in that example, that the Na and the water are the reactants, and then the NaOH plus H2 are the products. And so when we look at an equation, like I said, first thing we want to do is make sure if it's balanced and follow the law of conservation. And the way we do that is we count the atoms of all the species. So is this equation balanced? Does it follow the law of conservation? So I'll show you how I would start to figure out, and this is going to lead into balancing. I like to draw a squiggly line down from my arrow. The reason being is it helps separate my reactants from my products because we have to make sure they match up. Then for each element type, I'm going to keep kind of a tally. So we have hydrogen, chlorine, and zinc. So I'm going to add those tallies on both sides. And I'm going to keep them mirrored no matter how they're introduced so it makes sense in my head. And so now I'm going to look and count how many hydrogen atoms do we have on the left side? Just one. We have one chlorine and one zinc. On the right side, though, we have two hydrogen atoms because it's H2, one zinc, and two chlorines because it's Cl2. So does this follow the law of conservation? No, we're forming more hydrogen and chlorine, which means this is not balanced. So we need to use coefficients to balance it. Now, we never change, for example, in the formulas where we have these twos, we never change those values. They have to stay the same. We can only put coefficients in front of the chemical formulas. And so the way we do so is thinking about what needs to change. So we need to increase our hydrogen and chlorine. So what happens if we put a 2 in front of the HCl on the left side? Now we have two hydrogens and two chlorines, and we're balanced. So the balanced equation becomes 2HCl plus zinc goes to hydrogen and zinc chloride. So that is our balanced equation. Because if we were to do the same tally, we'd get two hydrogens, two chlorines, and one zinc on both sides. Any questions about that? Okay. So rules for writing chemical equations is that we need to know the formulas of the compound. So I already know I'm going to get some headaches and grumbles out of you guys today because Unit 3 is coming back. And so we're going to have to remember how to write formulas from names. We have to know how to balance the equation. And for balancing it, typically it's suggested that you use a pencil. So the way that I do it is I like to keep track of the changes I made like this. But sometimes it can get complicated. So instead of crossing it out, you could erase and change it to a 2. I'm not going to let you worry about, or don't worry about if you use a pencil or not. It's up to you. Write coefficients one at a time. That means if there's multiple things that have to change, only write one at a time, see what the change is, and then continue on. It'll keep things less messy. And only, again, here, I talked about this already, only coefficients can be used and revised when necessary. So one thing that I want to mention here is that if you can simplify all coefficients, do it. So what I mean is if you have species and they all have, let's say it's 2, 2, and 4, they're all divisible by 2. So simplify them. I'll write that as an example here. That's supposed to be a plus. Does that make a little bit more sense what I'm trying to say with an example? Sorry, I shouldn't use a reaction arrow here. Oh my, I cannot draw it out today. Okay, any questions on that? So just pretty much all coefficients divisible by the same number, do it. Okay, moving on. Something to think about, the diatomic elements. So we're gonna have to remember which ones those are. Those ones are because having 2Cl where you're just talking about 2 atoms of chlorine on its own versus you have a mole of diatomic chlorine. got to remember that those things are different. And the main thing I want you to remember about diatomic molecules, and this will make most sense with this example here, is that, okay, let's say we're talking about table salt, sodium chloride. In sodium chloride, we have a Cl- and an Na+. There's one of each. But if we show a decomposition reaction or showing them get separated, chlorine does not exist on its own. It's a diatomic element. So how we'll represent this is NaCl is going to Na plus Cl2. Because chlorine will not be on its own. That 2 is very important because it's diatomic. And so now this isn't balanced. So we need to balance it. And the way to do so is that we know we're going to have to put a 2 in front of NaCl because it only has 1 chlorine. If we put a 2 in front of it, now we have 2 chlorines. But then now we also need 2 sodiums on both sides. So on the right side, you're just throwing a 2 in front of there. And now we have our balanced equation. So I guess I'll write this separately as one balanced and one not, just I'm sorry, I know how crazy my chlorines look, but that is Cl. Okay, and so let's do some examples with diatomic elements. Starting with hydrogen gas and oxygen gas going to water. So again, I'm going to start with this squiggly, and we're keeping track of hydrogen and oxygen on both sides. On the left side, on the reactants, we have 2 hydrogens, 2 oxygens. On the right side, we have 2 hydrogens, but only 1 oxygen. And so one tell is that if you have an odd number, likely you're going to want to make sure, get it even so we can match up. So I'm going to throw a 2 in front of the H2O for fun. Now we have 4 hydrogens because we have 2 H2s, and then 1 oxygen becomes 2. So now on the left side, we have to adjust our hydrogens. Those aren't equal anymore. So all you have to do is throw a 2 in front of H2. Now we have 4 hydrogens and 2 oxygens on both sides. All right, let's do one with aluminum oxide. Splitting it down the middle, we have aluminum and oxygen on both sides. Starting materials, on the left, we have 1 aluminum, 2 oxygens. On the right side, we have 2 aluminums and 3 oxygens. So another nice thing to go for here, we have 2 and 3 oxygens. What's the lowest common denominator between those amounts? 6. So let's start by multiplying one of them to get to 6. So I'm just going to start on the right side with Al2O3. I'm going to give that a 2. That changes aluminum to 4, oxygen to 6. And so on the left side, now we just have to throw a 4 in front of aluminum and a 3 in front of oxygen. So I like to start by adjusting the molecules that have both of the compounds in there to see what my ending quantities would look like. All right, next one. Sulfur and oxygen. When you have oxygen or any element that appears more than once throughout, so in 2 different species or 3 or 4, you have to count all of them. On the left side, we only have 1 species, so we have 1 sulfur and 3 oxygens, but we have to make sure on the right side that we count oxygens from SO2 and O2. So we have 1 sulfur, 4 oxygens. So here, the lowest denominator is 12 between the oxygens. And so I'm going to throw a 4 in front of SO3. That means we have 4 sulfurs and 12 oxygens. On the right side, we have to now get that to 12, but we have to think about sulfur. The only way we can adjust sulfur is from SO2 on the right side. So let's put a 4 in front of that. Then we have 4 sulfurs. Then we have 8 that come from SO2 plus 2. So right now we're at 10. So not quite there yet. So we're going to leave the sulfurs alone and just adjust with the O2 and put a 2 in front. This brings our total now to 12. But are all coefficients divisible by a number? Yes, they're all divisible by 2. So really what we would want is 2SO3 goes to 2SO2 plus O2. Because if we were to think about both sides and count and double check, now we have 2 sulfurs and 6 oxygens on the one side. Again, 2 sulfurs, and 2 times 2 is 4 plus 2. We have 6 oxygens. So it still balances. We just always want to make sure it's the most simplified. Any questions on that process? Sweetness. Okay. Let's keep balancing. So calcium, hydrogen, nitrogen, oxygen. This one we have 4 elements to keep track of. On the left side, 1 calcium, 1 hydrogen, 1 nitrogen, and 3 oxygens. And so when we start working with things with parentheses, we have to remember to multiply everything inside the parentheses by that subscript. Calcium, we still have 1, but now nitrogen, we have 2, oxygen, we have 6, and we have 2 hydrogens as well. So I see I have 3 oxygens on one side and 6 on the other. So I'm going to try to multiply the thing that contains the oxygens by 2. Now we have 2 hydrogens, 2 nitrogens, and 6 oxygens. That's all it took to balance this one. Both sides are now equivalent. Moving on to the next one. We're working with aluminum, copper, sulfur, and oxygen. On the left side, we have 1 aluminum, 1 copper, 1 sulfur, 4 oxygens. On the right, bless you. On the right side, we have 2 aluminum, 3 sulfur, 12 oxygens, and 1 copper. So what I'm going to go ahead and try is multiplying the CuSO4 on the left side by 3 to try to get those oxygens to 12. We now have 3 coppers, 3 sulfurs, and 12 oxygens. This is not quite there yet. We have both copper and aluminum that we need to balance. And so I'm going to keep working with copper. So what's nice is on the right side, we can just add a 3 in front of Cu. Now our coppers are balanced. And we need 1 more aluminum on the left side. So I'm going to multiply aluminum on its own by 2. And so you guys should have gotten 2, 3, 3, 12 as your quantities. Any question on that guy?
Is there supposed to be a plus sign on the next one?
Yep. Mistake number 2. Don't worry, they caught that yesterday. So well, I caught it yesterday, I should say. This is what happens when I make these things at 10 p.m. at night. So working with iron chloride and lead nitrate. We are going to split this in half. List our iron, chlorine, lead, nitrogen, oxygen. So we have 5 species to keep track of this time. On the left side, we have 1 iron, 3 chlorines, 1 lead, 2 nitrogens, and 6 oxygens. And on the right side, we have 1 iron, 2 chlorines, 1 lead, 3 nitrogens, and 9 oxygens. So what I'm going to go after right now, instead of doing oxygen, is I'm going to focus on the nitrogens. I am going to give a 2 in front of iron nitrate on the right side. That's going to change iron to 2. That's going to change 6 for nitrogens. And then that's going to change my oxygens to 18. Then I am going to go back to the left side and I'm going to put a 3 in front of lead nitrate. Now we have 3 leads. Oh, not 3. Yeah, 3. 6 nitrogens and 12 oxygen. So I'm still not quite there yet. And one thing I want to pause and say, if your balancing reactions is feeling like it's kind of wonky and going back and forth, let's say the first thing you try is a mistake, that's okay. First of all, mistakes are fine. I make them all the time. Second of all, balancing equations isn't always just you know right away what to do. So I just wanted to put that caveat out there. Whatever you do, just keep moving stuff around, try new numbers, and eventually you'll find the path that works. Anyway, I'm gonna keep going. So right now we don't have the right number of oxygens. We still need to figure it out. So actually we do have the right number of oxygens. I can't do math. We have 18 oxygens. 3 times 6 is 18. And so what we're left with is that our chlorines don't match, as well as our irons, as well as our lead. So I'm going to tackle the chlorines right now because we have an odd number of 3. I'm going to multiply iron chloride by 2. Now we have 2 irons and 6 chlorines. And then I'm going to put a coefficient here. Sorry, didn't leave myself space of 3 in front of lead chloride. Now we have 3 lead atoms and 6 chloride. So this one took coefficients on all 4 of the species, but we got there. Any questions on this one? Okay. Now this is where I expect to be some sad faces. If I tell you that magnesium's mixed with lead 4 nitrate goes to magnesium nitrate plus lead, I expect you guys to be able to write out the chemical formula for this reaction. So I'll go through these with you guys. Don't forget that in your blue packets that you have your list of polyatomic ions. It's just up to you to remember, 1, when to recognize it is 1, and 2, how to find it off the list, find the charges, etc. So going through the first example, magnesium, its symbol is just Mg. We are going to add that to lead 4 nitrate. So if you were to go through your table and look through it, you'll find that nitrate is NO3 minus. So if you have lead 4, what does that mean? What does the 4 stand for? No, that is the most common mistake. 4 does not indicate a quantity. 4 is the charge, okay? So if you see Roman numerals, it means the charge. That means we have a lead atom that's plus 4. So if we know that each nitrate, remember this is a unit that doesn't split up, is -1, how many of them do we need? 4. So what this is going to end up looking like is PbNO3 4. Because we get a +4 contribution from lead, and we get 4 times a -1 contribution from nitrate, which we always want to make sure equals to 0. We have a neutral compound. Any questions on remembering how to do this? Okay. Then for magnesium nitrate, we're still working with nitrate, so we still have NO3 minus 1. But magnesium has what charge? Does anyone remember how to figure that out? Hint, it wants to have a stable octet or a full valence shell. +2. So however many spaces away from being a noble gas, the metals like to lose electrons. Or think of it as metals losing their valence electrons. How many valence electrons does group 2 have? Everything in group 2 has 2 valence electrons. It loses those 2 spots. So we get Mg +2. And we know already that nitrate is, I'm going to put that down here actually, -1. So how many nitrates do we need? 2. So then we put NO3, 2 plus lead. Any questions on that one? Okay. We're not going to worry about balancing these ones. You guys will have more practice. So then for the next one, we have lead 2 nitrate. So we're still working with nitrate. What would be lead 2 nitrate's formula? Yes. So we have a +2 from lead and 2 times the -1 from nitrate. We're adding that to sodium phosphate. So now phosphate is PO4 minus 3. How would we write this one? First of all, we got to figure out what's sodium's charge. Yeah, sodium is +1. It's just one away. So if we have +1 on sodium and -3 from phosphate, what should our formula be? Na3 PO4. Because we have 3 times a +1 charge from sodium, and we're adding that to the -3 charge from phosphate to get 0. Then for lead 2 phosphate, we should have Pb3 PO4 2. Do you guys remember the trick with the charges and the quantity of? Exactly. And so just to review, if we have lead 2, and we are trying to, figure out how many of each we need, the number of the charge ends up being the quantity of the other one. So notice how, sorry, I'm gonna have too many arrows here. So just a reminder there. And then we have sodium nitrate. What will be the formula of that? NaNO3, because they're 1-to-1 charge ratio. Question? Are you just itching? Okay, looks like you're waving high. All right, any questions on this? Okay, last thing I want to run over very quickly. These should be relatively easy for you guys to determine between. The biggest thing is just finding out the patterns. And so anything with oxygen, something plus oxygen, you're blowing it up. It's flammable. You're going to make a reaction. You need oxygen. This is why when your fire starts going out, you blow on it or wave something at it to try to get more oxygen flow into it. So CO2 in the beginning, if you see O2, not CO2, if you see oxygen gas, it's going to be combustion. Synthesis. If you synthesize something, you're making it. So here, if you're adding 2 parts to make 1, then you're synthesizing. Versus the other direction, decomposition, you start with one thing and you decompose it into its 2 parts. Then we have single replacement. And so for single replacement, only you have one compound and an element, a little switcheroo is going to happen. And what I mean is that copper will then switch in to be with something else, to be into a compound, and then silver in this case switches out to be on its own. So nitrate likes to get around. So we got to think about single replacement. I know, awful example. All right, double replacement. This is where you just switch partners overall. You have 2 compounds and you just do a switcheroo with partners. Potassium leaves at the hydroxide and goes with sulfate. And then, for example, here, hydrogen wants to go with what used to be OH, but now becomes water. So you're just switching the partners here. I feel like this example is a good one. Any questions